How about those dodgy 90s graphics at the end there? They were good. Welcome to the ASV September Astro Talk. Before we begin, I would like to say that in the spirit of reconciliation, the Astronomical Society Victoria acknowledges the traditional custodians of country throughout Australia and their connections to the land, sea and community. We pay our respects to their elders past, present and extend that respect to all Aboriginal and Torres Strait Islanders people today. Tonight's speaker is Stephi Bernardi, or Bernard, sorry, I've got that wrong. My apologies, Stephi. She will share with us the amazing technology of the Hubble Space Telescope, which has allowed us to view our first view of the first galaxies in the universe, showing us surprisingly bright, developed galaxies only 700 million years after the Big Bang. Stephi will explain how she looks for these galaxies and how the universe works against us in seeing them. But first, I'd like to welcome our President, Chris Rudge, and Stephi to the stream. Welcome, Stephi and Chris.
Good evening.
Now, following Stephi's presentation, we will be treated to a tour of the September night skies in preparation for this coming weekend's live stream extravaganza. 7 streams in 3 days. It's going to be hectic and crazy, but it's going to be fun. So for those on Facebook, make sure you're liking and following our page. And if you'd like to support and donate stars, every star donated helps us bring these streams to you. And if you're on YouTube, be sure to subscribe and turn the bell on so you don't miss any of our streams. Chris, over to you to introduce Stephi to us.
Thank you, Mark. Well, Stephanie Bernard is an astrophysics PhD at the University of Melbourne, and she's looking for the first galaxies to form in the universe, only some 500 million years after the Big Bang. And for those of you who can do simple mathematics, that makes it about 13 billion years ago. She's used some of the most powerful telescopes in the world to do this, including the very famous Hubble and the Spitzer Space Telescopes. And when she's got some spare time, she loves to knit colourful jumpers and hang out with her cats. What an admirable thing to do. Thank you, Stephanie. So over to you.
Yes. All right. Will you switch over, Mark? All right, can you see my slides?
We can indeed see your slides, yes.
Beautiful, excellent. All right, hi everybody. I'm really happy to be talking today. I was saying before we started that I haven't been able to give any public talks for a while because of COVID, so I'm really happy to be talking today about the work that I've been doing. My name's Stephi Bernard. As Chris said, I'm a PhD student at the University of Melbourne and also with Astro 3D, the ARC Centre of Excellence for All-Sky Astrophysics in 3 dimensions. So I'm going to be talking about how we look for the very first galaxies in the universe using telescopes like the Hubble Space Telescope. And I'm on Twitter at AstroStephi if you want to get in touch with me after the talk. So let's talk about the universe. And so when we're talking about looking for the first stars in the universe, we have 2 very important properties of the universe that I want to be keeping in mind. So firstly, the universe is expanding. We're in the stage of the universe where it's expanding at an accelerating rate due to dark energy. And in the universe, the speed of light is finite. So that means that as space is expanding, the light from galaxies that we're trying to look at is always traveling at a specific speed, the speed of light. So we can have a look at that using this little video. And this is from CASTRO, the ARC Centre of Excellence for All-Sky Astrophysics. And this is basically just showing us a little visualization of what that looks like. So when we talk about expansion of the universe, it's not that we are at the center of the universe, like this little galaxy here in yellow, and that everything we see is moving away from us. One sort of cool thing about the universe is because the speed of light is finite, the galaxies that are closer to us appear to have moved less or expanded less than the galaxies that are further away. So we're not at the center, because if we could move to a different galaxy and take a look at all the galaxies from that different vantage point, we would see exactly the same effect. So all the galaxies, including us, our original galaxy, will be moving away from that galaxy as well. So So we have a saying in astrophysics that the Big Bang happened everywhere, and so the whole of 3D space is sort of expanding out all the time. So because the speed of light is finite then, if we look at galaxies or objects in the universe that are further away, we're really looking at them as they were back in time. So in the solar system, this time delay isn't very much. For the sun, it's a few minutes, 8 minutes. But as we get out of the solar system, things get very far away very quickly. So when we're looking at the closest galaxies to us, these are a few million light years away. And then, as we said in the introduction, the galaxies that I want to be looking at, the first ones in the universe, are all the way back close to the Big Bang. So that's 13 billion years of time that we're sort of able to look back at, which I think is really cool. So how far can we actually see in the universe? Well, this is a question that really depends on which instruments we use to look at it. So we have, we can start with our human eye, which you guys are probably all familiar with if you're astronomy fans. So our eyes are very small. They're only, a centimeter square across. And also our eyes can't store up photons for a long time. So really the furthest thing that we can see with our eyes is the Andromeda Galaxy, which we sadly can't see here really from the southern hemisphere. But if you're in the northern hemisphere, you can see it. And it's, as I said, a few million light years away. So if we go to a bigger detector or a bigger mirror, like a reflecting telescope, like you probably would have used with the ASV. So this has a bigger collecting area, which means that we can get more photons and we can look at fainter things. So the furthest thing we can actually see with the telescope is this quasar 3C273, and this is, I think, 1 billion light years away. This is very far away. It's very bright and very small, so it just looks like a star really to us. If we go to the other end of the scale, a really big telescope out in space, so we can actually start to see a lot further, because telescopes with cameras, they can store up photons for a long amount of time, and also the wider collecting area allows us to get a lot more photons than something like our eye or even our consumer telescope can. So this is the Hubble Extreme Deep Field. This is the deepest image ever taken. I'll go a bit more into this later. And of course we have wavelengths play a really important part in what we can see. So far we've talked about optical wavelengths, but if we move to radio wavelengths, we can actually see all the way out to the cosmic microwave background, which is this image that you've probably seen before of sort of cold and hot spots in the very early universe, only 400,000 years after the Big Bang. And this is sort of our real proof that actually these sort of seeds of the first galaxies were there even just after the Big Bang, which is a really important discovery that won the Nobel Prize when it was discovered. So as we can see, using different instruments really just gives us a different view of the universe. And so if we take all of our different telescopes on the Earth, of which there are many thousands, we can actually start to look at different parts of the universe. So we can look at the close by galaxies, like many people study the internal Milky Way and the stars inside it. Or we can also look at all of the galaxies that are outside the Milky Way. And so this is a little zoom through basically of the locations of all of the galaxies that are known sort of in the universe. So we can see, as I said, that once we get out of our sort of solar system, the universe is very, very big, and also it's very, very empty. So galaxies are sort of rare in the universe. So now we're getting out to about 1 billion light years, which is sort of where that quasar was. And another thing we can start to see is actually that there are these things called clusters and voids. So you can see that there's some areas where there are lots of galaxies and some where there are very little. So now we're getting out to about 10 billion light years, which is getting closer to the area that I want to look at, sort of in the first billion years after the Big Bang. And you can see that we're getting fewer and fewer galaxies as we get further and further out. And so here we've added in a few more surveys, but you see the same thing, that there are lots of galaxies that have been discovered sort of closer to the Milky Way. And then as we get out, there are fewer and fewer that can be seen. And this is the Sloan Digital Sky Surveys. This is the data from almost 1 million galaxies. The two wedges you might have already figured out are the Milky Way itself, so we can't see in those directions. We can only see the northern and the southern hemisphere. And then this is the cosmic microwave background superimposed on top of it. So one of the big questions is this sort of lack of galaxies at the very, like the most distant galaxies, is this just because it's really hard to see them? Or is this something to do with the actual process of how galaxies form? Are there just fewer galaxies around then? Are they more rare? And this is one of the reasons why we want to actually look for them, because this will help us to test our theories of how the universe was evolving, especially at these very early times. So once we've got all those galaxy samples, and we can put them all together to actually get an idea of how the galaxy was forming. So we have sort of two parts to this diagram. We have the very first, so on the left, we have more of the theoretical sort of side where we have the quantum fluctuations and inflation and the Big Bang. But then after we get to the cosmic micro background, we can actually start to use our observations to piece some of these parts of the universe together. We have something called the dark ages, which I'll go into a bit later, but this is really when there were just no stars in the universe that were actually producing light for us to see. After some amount of time, around 100 million years, we think at the moment, the first stars start to form, and then it takes a little bit more time for there to be enough stars sort of in a particular place, gravitationally interacting, to call it a galaxy. So we think the first galaxies started to form in the first 500 million years after the Big Bang. And then after that, the universe is a really dynamic place. So galaxies are evolving, growing all the time until they become galaxies that are more like the Milky Way and other large galaxies that we see in the universe today, which is the part on the right where we are right now. So just highlighting this first stars number. Okay, so as I mentioned, we want to know about these galaxies in the early universe. So our current theory is that these galaxies are very small, just because, firstly, they're really far away. So it's the same sort of idea as if you have a candle in front of a face, it burns very brightly, you can feel the heat. But if that candle is about a kilometer away, you're going to have trouble seeing it at all if you can actually see it. So because these galaxies are, even if they're the same size as the Milky Way, because they're so far away, they're just going to look really, really small. But also, because these galaxies are new, they've only been forming for a fraction of the amount of time with the Milky Way, we think that they're actually going to be physically small as well. So that makes them really hard to detect. They're very distant, as I said, which makes them hard to see. And we think that they're very rare. So these are just the first galaxies that are starting to form. So it's not everywhere in the universe that's going to have enough stars that have formed at that point to start making galaxies. So this is one image from the Hubble Space Telescope in the background. So even though there are around 2,000 sources in the image, and sources just means anything that's a star or a galaxy or anything really that our computer programs will pick up as a collection of bright pixels, no matter what it is. We might have one, if we're lucky, early galaxy in each of these images. So they're really hard to find, which is why I've spent my whole PhD looking for them. So fortunately, we have Hubble to the rescue. And so this was launched in 1990. Hubble is really wonderful because it has a 2.4 meter mirror. So that's roughly the size of the room that I'm in right now, my dining room. And that is maybe not such a large mirror on Earth these days, but you have to remember that this was launched into space using a space shuttle. So 2.4 meters is actually a really big sort of payload to put up there. So it has really a wonderful array of instruments. It can do both imaging and spectroscopy from ultraviolet to infrared wavelengths. And so I'm sure you guys know about the importance of both imaging and spectroscopy to have a look at lots of different objects in the universe. So I thought I would just sort of go through a bit of the Hubble history, because last year was the 30th year of Hubble's operation, and it really wasn't, thought to have lasted nearly as long as it has. So it's really wonderful. So of course there was an initial setback. So when it was first launched, the mirror was the wrong shape because it had been ground to the wrong sort of shape. And so it actually made these images like on the left, which are not very much better than what you see from the ground. So with some upgrades in later sort of servicing missions, some extra optics were added in to correct for that misshapen mirror, and we started to get really wonderfully detailed images like on the right. Okay, so I'm going to sort of zoom out from our solar system, but one of the great things about Hubble is that we can get close views of our planets in our solar system here from Earth. We don't have to necessarily send satellites to these planets, although of course we love to send satellites because we can get so much more detailed information from being close up. This is on the left, we have comet, I think Schumacher-Levy 9, which collided with Jupiter a long time ago. I was a child, so probably 20 years ago at this point. And so these are some images with Hubble of the sort of development of how the impact site sort of happened over time. On the right, at the north, we've got, on the top, sorry, we've got an image of an aurora on Jupiter using one of the ultraviolet instruments on Hubble. And so this is similar to an aurora on Earth because Jupiter has a very strong magnetic field. And so using Hubble, we can actually see these from Earth. And then, of course, on the bottom right, we've got the best photo of Pluto that we could get before New Horizons arrived there in 2015. And so this is actually, reasonably detailed given just how tiny Jupiter is, and not Jupiter, how tiny Pluto is and how far away it is. I think this is really astonishing that they're managing to get these different maps of the surface all the way from Earth. Of course, if we move out, we can look at stars forming inside the Milky Way. This is the famous Pillars of Creation image. This is showing some gas clouds, which have stars forming at each of the sort of ends of these little big filaments. We can see amazing views. This is, I think, one of the most amazing things is we can see individual stars inside other galaxies. So I'm quite sure this is one of our nearby galaxies. I don't think it's Andromeda, but we can see actually the individual stars that are making up this galaxy along with the gas lanes, the darker sort of patches inside the galaxy as well. And this gives us a really good view of important sort of yardsticks for our sort of measuring of the universe, like Cepheid variables. Seeing them inside other galaxies gives us a really good distance to these galaxies. And so this being able to detect these is a really important thing that Hubble can do. If we go out even further, we can see huge clusters of galaxies. So these are some of the largest structures in the universe. And because these galaxies are very massive, they actually magnify the galaxies and warp the image that we see of the ones that are behind them. And so this is actually how a lot of very distant galaxies are found, because the magnifying makes them brighter. It just makes them a bit easier to see and detect. So this is really cool that Hubble can see this, and because it's got such amazing resolution, it can actually start to tease out some of the images of the galaxies that are behind getting magnified. And this is another view just of a similar galaxy cluster where you can see some of these, more of these arcs of galaxies that have been magnified. Okay, but the important discovery that Hubble has made for the field that I'm in is from the Hubble Deep Field. So I thought I would just go through a little bit of the history of this, because if you haven't heard the story, I think it's quite interesting. So back in 1996, the Hubble Space Telescope is run by the Space Telescope Science Institute in Baltimore in the US. And so that institution has a director, and they're basically there directing, the research directions of the center and also the Hubble Telescope operations. And so as sort of part of that, they get a dedicated amount of time on the Hubble Telescope that they can use for whatever they want to. So usually they'll take in the proposals that astronomers put in, and they might choose a few of them and decide that they are interested in putting their special time towards those projects. But in 1996, the director decided that he wanted to get an image basically of the blankest patch of sky that they could find. And so this patch of sky is really, really tiny. I'll sort of show you an image later on how tiny it actually is. But it's really the size of, if you had a grain of sand and held it at arm's length, that's the amount of sky that this is covering. So they wanted to find a patch of the sky that had no visible stars from the Milky Way, no visible galaxies. And a lot of people thought this was just going to be a waste of time. And, using and keeping something like Hubble sort of operating is very expensive. So they thought this was a real waste of time. And so he looked at this for, I think, a week straight. And a lot of people thought that this would just be a blank image. But of course, we know that actually the image that came out was this one. And so we see lots and lots of galaxies in this image. And this is, as I said, just one tiny patch of the sky. So this really implies that the universe is full of galaxies, which is not necessarily something that we knew at the time. So this is a really important discovery in our sort of extragalactic astrophysics. So this is 1 million seconds of time. And so this, as I mentioned when I was talking about how far we can see, this is just optical imaging. So using this image, we can see galaxies out to about 1 billion years after the Big Bang. So not quite pushing into that 500 million years that we want to see the first galaxies. So this is just that little comparison of how big the screen, the image actually is. So we've got our image of the full moon, which takes up about half an arc second in the sky. On the right, we've got what we call a wide field image, which is basically trying to get as large a patch of sky at a time as you can. This makes doing surveys looking for galaxies really efficient because you can look at lots of the sky all at the same time and build up a sample of galaxies very quickly by getting that amount of time. On the left, we've got a few different Hubble surveys, and you can see already that they're much smaller than the Cosmos image. And so the one at the very center that says HUDF, that is the size of the Hubble Deep Field image. So you can see that it's really only about 1/100th of the area of the full moon. So it's a very, very small patch of sky, but we still see all of these different galaxies. So before I go into trying to push into this 500 million year sort of threshold, or frontier, I guess, we need to sort of talk about a few of the effects that are hampering us from actually seeing these galaxies. So the first one is something called Redshift, which you guys may be familiar with already. But basically, because, as I mentioned, the universe is expanding and the speed of light is finite, that means that the light that is leaving a galaxy, as the space is expanding, that light is having to stretch out in its wavelength. And if you have a longer wavelength, that means that your light becomes redder. So we have that situation like this, where light is exiting a galaxy and it may be blue when it leaves, but because the space is increasing and the wavelength is also increasing, when it reaches us, it's actually got a wavelength in the red sort of wavelength regime. And of course, when we are looking at the very earliest galaxies, the universe has expanded a huge amount. And so what we are struggling with is that light that might be emitted at ultraviolet wavelengths by the early galaxy, which is bluer than what our eyes can see and bluer than our optical wavelengths that we've been looking at so far. It's actually detected by us at infrared wavelengths, so even redder than what we can see with our eyes and redder than our optical instruments. So we have a problem that infrared light is blocked by the atmosphere, just because we have lots of water in our atmosphere and other molecules, and they really like to absorb infrared light. So we need a telescope that's above the atmosphere to actually see this light in the first place. So fortunately, Hubble is already there. But then we also have a problem where the universe is full of hydrogen. And so this is probably not a surprise to you all, but hydrogen, when we're talking about infrared light, is actually a big problem for us. So at the bottom here, I've got a sort of sample spectrum of a galaxy, and this is at infrared wavelengths. So we're going from 800 angstroms to 1600 angstroms, or 80 nanometers to 160 nanometers. We see that we have a few emission peaks in the spectrum. The important one is the one that's just redder than 1200 angstroms. This is called Lyman alpha, and it's a very important emission line for us as high redshift astronomers. So if we imagine the galaxy on the left, and that galaxy is emitting light that's going through the universe. So all of this different sort of web, sort of bright material that you see towards the right of the galaxy, this is representing the hydrogen in the universe. So we'll see what happens as our photon passes through the hydrogen. Okay, so as it passes through each different little layer of hydrogen, you can see that some of the light from the spectrum starts to get absorbed. And that means that as the galaxy is getting further and further away from us, the ultraviolet light that it's emitting is just getting sucked up by the universe. And we actually don't see that light. So sometimes it hits really dense parts of hydrogen, and it'll absorb a lot of the light. But basically, the further we go back into the universe, the more of this light at ultraviolet wavelengths gets absorbed. And so this is really frustrating for us as high redshift astronomers because, as I mentioned, the redshifts are so great, or the stretching of light as the universe expands is so great, that if we want to see these galaxies at all, we have to be looking at the ultraviolet light that's being emitted by the galaxy. So it's very tricky, but we have developed some very clever ways, I think, of dealing with the problem. One of them is that we can look for a particular type of galaxy called a Lyman break galaxy. And so this is really what I do my research on. So again, we have a model spectrum, this time in the top sort of part, and that's in the gray sort of filled line. And then we also have some colored sort of filter curves superimposed on top of that. And each of these is a different Hubble filter. So the numbers basically indicate the weight of the nanometers that each is looking at. So on the purple line, we've got the blue light, optical, and then we're going through the red light and sort of where the dashed line is at 1 micron. That's sort of where we get into infrared light. And so at the bottom, we have some simulated images of how this particular galaxy would look at each of these different filters. So we can see that this galaxy, it's emitting a lot of light, basically all the way from blue light out into infrared. So it's clearly visible in all of our sample images. But if we send this galaxy back in time, we can see what happens to the images. So we can see that as it goes back in time, it's being redshifted just so much. Ooh, no, sorry. It's being redshifted so much that actually all of this ultraviolet light that the hydrogen is absorbing is actually falling out of these bluer wavelength bands. And we're actually getting into the, I think it stops, yes. Okay. So eventually, as we get into this, it says Z equals 12. That just means redshift. This Z equals 12 is really, you can think of this as sort of the 500 million year after the Big Bang sort of barrier. So as we get into this very early universe, our galaxies are only visible at infrared wavelengths. And really the ones that we are very interested in, they're only visible in the most red infrared filter that Hubble has. So not only are these galaxies small, distant, rare, but we just don't have the technology really to actually look at them aside from this very red Hubble filter. So this is a very frustrating thing to try and observe because you're really trying to not see it at all of the other wavelengths that Hubble has and only detect it at the very reddest wavelengths. So it can be quite tricky. And I'll just play this one more time if you want to see the galaxies disappearing again. So if you're wondering this sort of line that's there now, so where the we call it the break, basically, that's where the Lyman break name comes from, where the spectrum stops emitting light. This is at that 1200 angstrom emission line, basically, that I showed in the previous video. Basically, the light that's redder than that that's being emitted by the galaxy is fine, but the only light that's bluer than that basically just gets gobbled up by all the hydrogen in the universe. So we can take our observations of all of these different filters, and we can actually reasonably simply separate our different objects that we see in our Hubble images into different ages, basically. So in general, the very bluer objects are less than 5 billion years old. The galaxies that we see more in the sort of yellow into the near infrared generally are between 5 billion to 9 billion years old. And then the objects that we only see really in the very reddest infrared filters, these are the more than 9 billion years old, or sort of the galaxies that are in the first 4 billion years of the Big Bang, 4 billion years after the Big Bang. And this is really, really like neat, I think, way of sort of doing an initial sort of separation of all the galaxies and filtering out what you want to see in the images. So the reason that there's just so much hydrogen in the universe, and the reason why these galaxies get really hard to see as we get out to higher and higher redshifts is because of this thing called reionization. So, so this is a period in the universe, and this sort of corresponds to that dark ages that we had in the sort of overall map of the universe that I showed earlier. We had the Big Bang, and then the universe was in a hot and dense state. We had expansion of the universe, rapid expansion, and it cooled down. But then there were no stars at that point. There was really just hydrogen, a little bit of helium, a very, very small proportion of other elements. And so it just took a long time, actually, for all of that hydrogen to start to coalesce and form into the first stars. So once those first stars start to burn, we think that they are very massive because there's just lots of hydrogen that they have to actually form. And they start to emit lots of this ultraviolet light that hydrogen loves to gobble up. And so once this process takes place and all the hydrogen sort of gobbles up all this light, then it makes the universe really easy to see through. But of course, the galaxies that we want to see, the very first generation of galaxies, that's smack bang within this reionization period. And so all this hydrogen makes it really hard to see the galaxies. But this period of reionization is an important part of the universe. So we want to find the galaxies because we want to see what was actually around then, because we want to know basically how this process happened, that the galaxies sort of did this thing called reionizing the universe. So even though it's hard, it really is worthwhile trying to find them. And so as we start to look at more and more distant galaxies, we can make up a new sort of map of the universe. This one's sort of putting more emphasis on that very early time. So on the left now we have us in the modern universe, and we can look out to further and further, or closer and closer towards the Big Bang, we can think of it. So our first frontier was the Hubble Deep Field back in 1996. So because this was only looking at optical light and no infrared, we could only see out to about 1 billion years after the Big Bang. The Hubble Ultra Deep Field, which was taken in 2010, that can push out further because that now has infrared imaging that it can do. And I'll talk a little bit about that in a minute. And then we're really starting to push into this first galaxy's first star sort of period, but we just can't quite reach it yet with the capabilities that Hubble has. So this is the picture of that Hubble Ultra Deep Field. So you might already see that this is a bit more crowded than the original Hubble Deep Field image that I showed. And that's just because this is using both optical imaging, like the Deep Field image was, and then it also has near-infrared imaging that was really unlocked by Hubble's last servicing mission back in 2009. So a new camera was installed on Hubble, and this had those infrared wavelengths that we were missing beforehand that we really need to be able to see the most distant galaxies. And so with this, we can now finally, in the last decade or so, start to actually look for these galaxies. Okay, and so these are some examples of the galaxies that have been found so far. So these are from the original Hubble Deep Field sort of paper. These are the most distant ones that were detected. And you can see that these don't look like very much. They're in the little sort of cutout images that I'm showing. And you can see that these galaxies are really only a few pixels across, even in these very deep Hubble images. So when I say these galaxies are small, I really mean they're very, very small. They're very hard to pick out from. You can see that there's lots of noise in the image sort of around the galaxies. There's lots of just stuff in between us in the universe and these galaxies. So it's very, very likely that you'll have some other galaxy in between us sort of covering it up and making it impossible to detect. And yeah, it is very, very tricky. And that's partly why I showed you all those beautiful Hubble images before, because this part of doing Hubble data sort of analysis is not very beautiful at all, I will say. So this is another little video, and this is really a zoom in of these two little galaxies and how they sort of fit into the big picture. So this is sort of just a wide field image of the sky. So one of those ones we are trying to get as much area as possible, but not necessarily a very deep image. And we can start to zoom in. So you can see just how big this image is. This is actually a few constellations, and you know how big constellations are in the sky. They're many degrees across. So we're zooming in, getting more and more detail as we get into deeper images, and getting into a smaller and smaller field of view as we go in until we get to the Hubble Ultra Deep Field. So this is, again, just a grain of sand really across the sky. And now we're going to start to separate these galaxies into the different ages that we've determined using this Lyman break method that I mentioned earlier. So you can see, as I mentioned, the bluer ones tend to be the closer ones. And then we sort of get into the more yellowy sort of ones. And then at the very end, we're really left with just the sort of red stuff. And so this is that little galaxy, only a few pixels across. And it's just really tiny and really red, because that's the best view that we can get of these galaxies at this point in time. So these are some other examples. As you can see, they all look very similar. So trying to get any information about actually, what we call the morphology of the galaxies. So are these spiral galaxies? Are these irregular galaxies? We don't expect them to be elliptical galaxies because we know it takes a long time for elliptical galaxies to actually form in the universe. Sorry, my cat's behind the computer. You may hear some noises from her. But as of, actually, I think that now should be up to about 2018, because I think there may be more now, but certainly less than 50 galaxies have been discovered at around 500 mega years, so 500 million years after the Big Bang. And if you remember the video that I showed at the beginning, or towards the beginning, the Sloan Digital Sky Survey has 1 million galaxies, and of course we've got other galaxies from other surveys. So there are millions and millions of galaxies known in the universe, This is a very, very small number, sort of out of all the galaxies that we know. One of the interesting things that we found about these galaxies is they're really remarkably bright. So they're about the same brightness as our own Milky Way, but they're really about 100th of the size. So what that tends to imply is that these galaxies have formed from very bright, very sort of blue young O stars and A stars. So the stars that we rarely see in our own galaxy, just because our galaxy is so old, that those stars tend to have already lived out their lives and become supernovae. So because these are so close to the Big Bang, those very bright stars are just taking all the hydrogen that's around and forming really fast. So I think that's a really cool sort of discovery that we've made about the early universe. I've sort of highlighted currently the most distant galaxy, but of course it's very hard to get information about these galaxies. Trying to do spectroscopy of them is really difficult because these are just so faint. And some of you may know that if you do spectroscopy, you're taking the very faint object and then you're trying to split out that light into lots of different wavelengths, and that just makes each individual wavelength even fainter. So it takes a huge amount of time to try and get spectroscopy of these. So at the moment, the imaging really is the best that we can do. There's also possibly more than we expected of these galaxies at the early universe. And so that has really important implications for our understanding of how the early universe evolved. So, we have these theories of how the universe is evolving, our cosmological theories. And having more than expected is sort of interesting because it means that possibly things like our, how many stars are forming in the early universe, that relates to, how dense the early universe was at certain points. And so it's all sort of tied in. And so solving that mystery, maybe it's just that we have a lot more contaminants than we thought we did. So galaxies that are closer to us that look like faint galaxies, or even, stars that are really faint can look like these faraway galaxies. So untangling all of that is really important to actually figure out if this is a real effect as well. So at the moment, the early universe is still a real mystery because it's just so hard to look at. However, we're really lucky in that the James Webb Space Telescope is hopefully launching this year. I have heard rumors that it'll be next year, but fingers crossed. So one of the great things, or many great things about the James Webb Space Telescope, the first thing is that it's 6.5 meters across. You might remember that I said the HST, or the Hubble Space Telescope, is only 2.3 meters across. So this is really an extremely large increase in collecting area. And we know that collecting area means that we can look at fainter objects, which is really great for these very small, faint objects that we're trying to look at. The other really important thing about the James Webb Space Telescope is that it's going to have more infrared wavelengths that it can look at. So this is the Hubble Space Telescope. This is the same as the Lyman break galaxies video that I showed you, but with just fewer filters to make it a bit easier to see. So again, we're going from blue wavelengths at the left to the very red infrared wavelengths at the right. And this is how a galaxy at around 1 billion years after the Big Bang in the first set of images, and then a galaxy at around 500 million years after the Big Bang would look in these images. And so as we can see, that galaxy at 500 million years is really only visible in the reddest wavelengths that Hubble can currently look at. But with James Webb, we're adding at least 4 new filters in the infrared. And so this means that we can get a much better view of these galaxies in the early universe. So the galaxy at 500 million years after the Big Bang, now you can see it in 5 different filters. And this is really great because it means that we can firstly verify that this is really a galaxy where we think it is, and not just some nearby galaxy or even faraway galaxy, but not nearly as far away as we want to be looking at, that just happens to look the same. These different filters will allow us a much better way of actually discerning between these different types of objects. But then we can start to look at even further away objects that have an even higher redshift that takes us out of the Hubble range. So we've got galaxies at z equals 12 and z equals 15. So this is really, you can think of this as more like 300 million years, and then even getting into 200 million years after the Big Bang. So really getting into this area where we think the first galaxies are starting to form. And you can see that even for these really, really far away galaxies, we still have enough infrared coverage that we can actually see these galaxies in multiple of these different images. So we're still able to get a really great view of these even earlier galaxies than what we can see with our current technology. So this is really exciting. Hubble and James Webb has so many other instruments as well that it's going to make it really great for looking at these different objects. It should be able to do spectroscopy of these objects, which we really just can't do at the moment. It's it's really, really difficult. So like opening up a whole new field, making it easier to find these very far away objects, and helping us to actually refine our view of the early universe, seeing if it actually agrees with our cosmological theories, which we just haven't been able to do at the current time. So really exciting time to be looking for these early galaxies. We have a team at the University of Melbourne who's looking at this, and we have international collaborators sort of all over the world, in the UK, in the US and in Europe, and in Japan, who are all doing this, sort of preparing for these searches, and it's really an exciting time to be looking at it. So that's my talk. Thanks everyone for listening, and if you've got questions, I think I'll be here for the rest of the night to talk about it.
We do. We have questions. I'll scroll back through.
Thank you, Stephanie. That was very interesting, and certainly expanded my knowledge about the universe. Thank you.
Now, Bipin on YouTube wants to know, how is the age of a galaxy determined?
Yes, absolutely. So I'll go back to my little video. So this is really the meat and bones of what we do as early universe galaxy explorers. So I may have sort of rushed through this a little bit, but basically the images at the bottom, these are the important things. So when we take a galaxy survey, we design it so that we have images that are taken of the same patch of sky in multiple different filters. So we may not do all of these different things. Usually we do maybe 4 or 5, because observing with Hubble is very expensive. So we sort of want to make things cheaper if we can. So for the early universe, we usually start with this yellow filter, this one that says 814. So this is really in the red sort of wavelengths, sort of at the edge between optical and near infrared. And then we'll get these ones that say F105 W and onwards. These are the really important ones for this early universe work. So I'll try and pause this at the appropriate time. Snow. Okay. No. There it is. I obviously haven't done this for a little while. Okay, so I'll stop it here. So this Z number, this basically means how much the universe has expanded since, well, it's sort of the opposite. It's more like how small was the universe at that time compared to how big it is now. So as the number gets bigger, we're getting closer and closer to the Big Bang. So that's all you really need to know about that. So this says Z equals 7.85, and I can tell you that means that this sort of simulated galaxy that we're looking at is about sort of 800 million years after the Big Bang. So what you see in the images is sort of the important thing. So these images each correspond to one of these filters. It's sort of a bit hard to see them because the filters are all on top of each other. That is on purpose, so that you get some of the same wavelengths in images that are sort of in filters that are next to each other. That's complicated. I can go into that later if you're interested. But basically, this simulated galaxy, we can see it in these 3 most infrared filters. We can see it a little bit in this F105 filter, the orange one. And then everything that's bluer than that, we don't see it at all. So basically, depending on which image we see it in, so if we go even further, we can see that it starts to disappear from this F105 filter. And it's starting to disappear again in this F125 filter. So basically, depending on how visible it is in each of these separate filters, that gives us a different idea of how old it is. So the ones that are further sort of, closer to us, they have a lower Z value. We can see that they're visible, really in most of these different wavelengths. So they only disappear really out of this very bluest one. And then it's as you get further and further away from us, you start to see fewer and fewer filters. So really that's all we do essentially. We just we take our images that we get from our surveys in these reddest filters, and then we try and find objects that appear in those reddest images, objects that are sort of in this next one, but sort of fainter. And then we want to make sure that we don't see it in any of these other ones, because that means that it's likely to be at higher redshifts, because we know that there are lots of different types of objects in the galaxy. All of them have different types of spectra that come from so many different things. Again, I can talk about that for hours if you would like, but generally we would expect to see something that's closer to us, more, sort of back here. It will sort of, even if it's sort of bright in these images, it will also be bright over here. So we really want it to not be visible at blue wavelengths and only visible at red wavelengths. And just depending on which images it appears in, that's how we tell the age.
Good answer. We've got another question from Amy, who's actually Bob. We found out. Sorry, Bob. Are there galaxies we will never see because they are moving faster than the light that is coming to us?
Yeah, so this is something called the observable sort of universe. So we know that the universe is expanding, and one of the things which is sort of like hard to understand is that the expansion can become what's called superluminal. So I had this sort of video about sort of illustrating Hubble's Law, which is basically that galaxies that are closer to us, they look like they're traveling away from us at a slower speed than the ones that are further away. You can see that there's a bigger distance between the ones that are further away than the ones that are closer to us. And so you eventually get to a point where the galaxies are moving so fast that it's past the speed of light. So definitely there's sort of an edge to the observable universe that we can currently see. So there's definitely parts of the universe that we're just never going to be able to see. Yeah, which is a shame, I think.
Yeah, we're missing out on a lot of stuff that if you don't know about it, you can't miss it, but still, it'd be nice to know. Neil wants to know, so the first galaxies seen in UDF, are they small because of their distance, or are they actually small, or is it both?
Yes, that's a really good question. So I tried to expand on this, but it's sort of a bit of a technical thing that's happening as well. So yes, the galaxies that we're looking at in the early universe, they are physically small. So when we measure their size, which we can do just from the images that we take, and we have to apply our sort of cosmological models to get how big they actually are, we can tell that they're only about 1 kiloparsec in size. And so if we think of the Milky Way, we're about 8 kiloparsecs away from the center of the Milky Way, and of course it goes out to 30 kiloparsecs, or about 100,000 light years. So these galaxies are really, they're much smaller than the Milky Way themselves, and that's just because they haven't had enough time to build up what we call the stellar mass, so the amount of stars that are in them. And then also we know that galaxies evolve over time by merging. So if we have two smaller galaxies and they collide, over time they'll merge into a larger galaxy, and that's how the big galaxies like the Milky Way become as big as they are. And the bigger galaxies, like elliptical galaxies, they're formed from the mergers of two galaxies like the Milky Way, two really big galaxies to form one huge galaxy. So yes, these are physically small, but they are distant as well. So of course, yes, if we've got something that's further away, it looks smaller, sort of in like what we call the angular size. So basically, if you have a triangle going from one edge of the object and then to the other edge of the object, the angle that your triangle is making is what we call the angular size. And so as things go away from us, that angle gets smaller and smaller, and the object looks smaller and smaller in our vision. But one of the really cool and weird things about the universe, which sort of blew my mind when I first learned about it in graduate school, but because of the way that dark matter has affected our expansion of our universe, there's actually a point where rather than objects getting smaller and smaller in our vision, they actually start to increase in their angular size. So they start to look bigger again. So these galaxies, they are very small, but we do have an advantage. And like, if that doesn't make 100% sense, like that's fine. It's very confusing what I've just said. But basically what you can think of is it's basically about halfway back in the universe's time. So things start to look smaller and smaller, like a galaxy that's a particular size will look like it's taking up fewer and fewer pixels on my image up until about halfway through the galaxy, through the universe's sort of time. And then as it gets further and further away, it will start to take up more and more pixels again. So we do have the advantage that these galaxies, because they're so far away, this effect is quite large. So they are looking slightly bigger than they would ordinarily, which makes it slightly easier to see. But of course, that's counteracted by them just being very small physically. So really, it's all sort of a wash, and they're just hard to see.
Now, Lee, how much bigger is the furthest universe expected to be seen on James Webb compared to Hubble? Do they know that?
Sorry, can you repeat that?
How much bigger is that furthest universe expected to be seen on the James Webb compared to Hubble?
The galaxy?
Yes.
Yeah. Yeah, so, okay. No, keep going. Okay, yeah. So this is sort of, again, this is like a simulated image. These are not real images of galaxies, but it's the same idea as the video that I showed before. So the top row of images where it says z = 10, that's currently what we can see with Hubble. And so the galaxies in there are very, very small. And the thing about these redshift numbers that I've got written, as you get further and further away from us, or closer and closer to the Big Bang, changing from like 10 to 11 to 12 is actually not taking up as much time as it does sort of getting to that point. So sort of we've used our optical sort of Hubble image to go all the way back from, all the way back from us to about 1 billion years after the Big Bang. And then, yes, so we can see from this image now that adding those initial infrared wavelengths in is taking us only about 300 million years closer to the Big Bang. So there's not a huge amount of time for that sort of effect of increasing angular size sort of at this stage. So the galaxies that we see with the James Webb, I expect would be a similar size to the ones that we see with Hubble. And of course, there's all this individual variation. Some galaxies are bigger than others generally. So I wouldn't be able to give an absolute answer at this point, but I would expect them to be pretty similar to what we see with Hubble, if a little bit smaller.
So a little bit further back than what we're currently seeing, but not much.
Yeah, so I don't know if you can see my cursor.
Yes, we can. Yes. Yeah.
Oh, yeah. I actually can't see it. So
no, we can.
Where is it currently?
That's right above Hubble.
The Hubble telescope?
Yes.
Look, I'll just go back to this view so I can see it. Okay. Yeah, so this is where we currently can see with Hubble. So with James Webb, so we're probably only going to get another couple of 100 million years on this. So, that's taking us all the way to, 200 or 300 million years after the Big Bang. So, like, as we get closer and closer to the Big Bang, things were happening at a really fast rate. Sort of once we get past this sort of first billion years of the universe, stuff happens sort of pretty slowly. So we just have galaxies sort of merging and growing bigger and new stars forming and all that sort of stuff, but it takes a long time. So this period of the universe that we're trying to push back into, this is really the sort of exciting sort of part, I would claim. Other people would not. But so yeah, even pushing only another 100 or 200 million years back into this time is really going to change sort of what we see. So yeah, while I don't expect the actual galaxies that we see at this point to be particularly different, it is really sort of what we can actually determine about them that is important. So if we can determine how bright they are, how big they are, how many galaxies there are at these early times, all that goes into sort of adding into our cosmology to make it more accurate, and of course, building into sort of our knowledge of the early universe and what happened just after the Big Bang. Yeah.
I think we've got time for one more, and that's Mikhail. Enjoyed your presentation, Steph. Thank you. What are your thoughts on the likely end of our universe? The big rip, the big freeze, or crunch?
Yeah, so when I was a child, I read a lot of astro sort of books, including my mom's sort of high school physics textbook, which had a lot of this. So it was really interesting back in, the reading books from like the 90s and even earlier, where this question was really like, was really debated because it just wasn't clear what was going to happen. So the discovery in the 90s about dark energy has really sort of not settled the issue, but it has sort of added a spanner to the works. So the difference between the different outcomes, the big rip, the sort of crunch, and then just sort of like forever expanding into, the heat death, is the density of the universe. And so if the universe is really dense, the idea is that the expansion of the universe, not acceleration, just expansion, can be overcome by the density, and then it will start to sort of not implode, but it will start to sort of collapse back into a singularity like the Big Bang. The Big Rip, I think, is I forget the details, but it's similarly to do with, I think, the density, whereas the heat death is more like if there's just not enough density for this to happen, then the expansion will just continue forever until we mentioned before that we have this observable universe where there's things that we can't see because they're just beyond what we can actually view. And so, after many, many billions of years, all of the galaxies that are not in our sort of local group or local cluster are going to be beyond that point. So we won't see anything in the universe apart from what's gravitationally bound to us. Dark energy means that the distribution of density sort of between matter and all these different things has changed over time. And so I think these days the sort of heat death situation where it just keeps expanding is the most favored because we can actually measure how dense the universe is by looking at the curvature of space. And at the moment it looks very flat, which means that it's not dense enough that it will form a big a big crunch, and it's not sort of underdense either and sort of closed. I think at the moment what I think is probably the sort of just gradual falling apart of everything until there's just us really left in the universe that we can see. Yeah, which is a bit sad. I think we're in a good time to be looking at the universe.
I've heard that we are, so that's glad to be alive while we can see some interesting things. Now,
I said this part was sort of boring, but it does mean that we don't have, all of the sort of more volatile stuff happening in here happening to us. We can just sort of observe it from our nice comfy Earth.
From the safety of Earth.
Yeah. Safety of the Milky Way.
Thank you very much for the talk tonight.
That's all right.
Everyone's enjoyed it. I enjoyed it, that's for sure. We've got Stephen with us at the moment now, who's going to give us tell us what's in the sky in September. So, Stephen, the floor is yours.
Beautiful. All right, can you hear me and can you see my full slides?
Yes, we can.
Beautiful. So, yeah, I'll give you guys a bit of an overview as what we'll see in the night sky during this month of September. And I'll start off by talking about some of the solar system objects, and then I'll talk about some of the deep sky objects, galaxies and nebulae. So this is the first time that I've given this sort of overview, and I'm a little bit biased. I'm mainly an astrophotographer. I'm not really a visual astronomer that much, so apologies if it's a little biased that way.
We'll forgive
so the
you.
first, sort of notable event will be in a couple days' time, on September the 10th, when the Moon and Venus will be in their closest conjunction for this time of the year, with only a separation of around 4 degrees. So you can see here that if you have sort of a wide angle lens, or even a very wide telescope, you'll be able to get both of these objects in the field. And Venus is in a sort of a gibbous phase at the moment. So if you've got a telescope with a lot of focal length, you might be able to make out some of the shape of Venus. Then also on September 10th, there's a comet in the neighborhood, Comet 4P Phae, and it'll be reaching its perihelion, its closest point to the sun. This comet's pretty faint. It's around a magnitude 11, so you'll need probably dark skies or a large aperture telescope to make it out well. The comet itself, the nucleus is around 3.5 kilometers in diameter, so it's fairly modestly sized. It has a period of around 7 years. Looking at it from Melbourne, it'll be about 32 degrees in altitude, located in the constellation Taurus. So it's a bit of a challenging one, but if you're a comet hunter, keep an eye out for that. Then on September 12, a large asteroid known as Pallas will be at its opposition. And Pallas is actually the third largest known asteroid in our solar system, with a diameter around 513 kilometers. So it's really quite a monster. It's got a period of around 4.6 years, and its magnitude 8.5, so it should be a lot brighter than the comet. So if you want to image it, it would be great to do sort of a time lapse over the course of the night, where you'll be able to see a bit of its motion relative to the stars in the background. It'll get to about 53 degrees in altitude at midnight, and you'll find it in the constellation Pisces. Then on September 14th, Neptune will be at opposition. It'll be located in the constellation Aquarius, around 10 degrees away from the bright star Hydor, and it'll reach around 56 degrees in altitude when viewed from Melbourne. Its distance at this time will be around 28.9 astronomical units, translating to over 4.5 billion kilometers away from Earth. And you'll definitely need a system with a lot of focal length in order to resolve any of the disk shape. But even with a more modest telescope, you can definitely make out the distinctive blue coloration. Then on September 21, we'll have our full moon, or as it's known in the northern hemisphere at least, the harvest moon. The moon will be located in Aquarius, and it'll only be around 3.5 degrees away from Neptune. So again, if you've got a sort of more wide lens or telephoto lens, you'll be able to get both the moon and Neptune in the same frame. And it's called the harvest moon because it's the closest full moon to the autumn equinox in the northern hemisphere. Then on September 15th, which you'll see on the left, Io will transit in front of Jupiter along with the Great Red Spot. And on to September 27th, Ganymede will transit in front of Jupiter along with the Great Red Spot. So if you're an astro imager looking to image Jupiter, this would be a beautiful sort of transit to image, and something that would be nice to do a time lapse of as well, to get a bit of that motion in there. So moving on from the solar system objects to deep sky targets, I'll start with some of the southern deep sky targets. And before I get into this section, I just want to say that upcoming on this Saturday, we're doing a live stream where all of us astrophotographers are going to get together and live photograph all of these objects. So if you're interested in coming along and seeing some of these objects live imaged, please do so. So the first object that I'll talk about is the Helix Nebula, NGC 7293. So on the right at the top here, this is its altitude over the course of the night. So you'll see it'll reach its highest point at around 74 degrees at around 11:40 p.m. On the bottom right-hand corner, I'll show a simulated field of view that you'll see with a sort of modest telescope and camera setup. Here I'm just showing an 8-inch reflector with a focal length of 800 millimeters and the very common ASI 1600 4/3 sensor. So this is what this object will look like in that field of view. And here's a nice, highly detailed image of the nebula itself, which was actually imaged by one of our members, Andy Candle, in 2018. So the Helix Nebula is a planetary nebula located in Aquarius. It's around 650 light years away, magnitude 7.6, so one of the brightest large nebulae available in the sky. And it's around 25 arc minutes in apparent size. So it's a really fantastic object to look out for. The next one is the Fighting Dragons Nebula. This is an emission nebula in the constellation Ara this time. It's around 4,000 light years away, and it's quite a large object at around, with essentially just the heads of the dragons being around 20 arc minutes by 12 arc minutes. So you can see at the bottom right-hand side what that field of view would look like. And you can see in the nice detailed picture on the left-hand side, down towards the bottom right-hand corner, there's another sort of interesting object down there. And I'll just leave that as a bit of a teaser. If you want to find out what that object is, please come join us in our live stream. So the next one, NGC 55, the String of Pearls galaxy, is a really beautiful barred spiral galaxy in the constellation Sculptor. This one's around 6.5 million light years away. It's magnitude 8.8, and it's relatively modestly sized, around 32 arc minutes by 6 arc minutes in width. So it's a nicely sized galaxy for imaging and relatively bright as they go. And as you can see in the top right, its altitude, it'll get up to 88 degrees around midnight. So this is a fantastic time to be imaging this target. The next one, NGC 300, the Southern Pinwheel Galaxy. This is an unbarred spiral galaxy, again in the constellation Sculptor. Similar distance, around 670 million light years away. But this one's a bit dimmer, magnitude 9, and it's a little bit smaller, around 22 arc minutes by about 15.5 arc minutes. Again, another beautiful target to image, and one that we'll be imaging on Saturday. NGC 253, the Sculptor Galaxy. This is one of the most beautiful galaxies visible in the Southern Hemisphere. It's an intermediate southern spiral galaxy in the constellation Sculptor, around 11.4 million light years away. It's magnitude 8, so pretty bright as galaxies go. And it's modestly sized, again, around half a degree in length and 6.8 arc minutes in width. Next up are the galaxies of the Grus Quartet, located, of course, in the constellation Grus. And these are a quartet, 4 interacting galaxies located around 50 million light years away. So on the left here is a partially finished Hubble image of one of the galaxies in this quartet. But as you can see on the right-hand side, when us amateurs image it, we mostly get a wide field of view, and we can image all 4 of these at the same time. Now a bit of an interesting one, NGC 246, the Skull Nebula. This is a planetary nebula located in Cetus, around 1,600 light years away. It's magnitude 8, so fairly bright planetary nebula, but it's also fairly small at only around 3.8 arc minutes in diameter. Another planetary nebula, Robin's Egg Nebula, NGC 1360. This one's located in Fornax at around a distance of 1,500 light years away. It's magnitude 9.4, so a fair bit dimmer, and it's roughly similarly sized at around 11 arc minutes in length, 7.5 arc minutes in width. So now I'll talk about some of the northern targets. So these are some of the targets that are a bit harder to see from Melbourne, but lucky for us, we've actually got a member up in Queensland, Caleb, and he'll be helping us image some of these really northern targets which we have really struggled to see from Melbourne. So the first one we'll be looking at is M56, the Ring Nebula, a beautiful planetary nebula located in Lyra, near the bright star Vega. It's at a distance of around 2,280 light years. Its magnitude around 8.8, and it's really quite small at only around 3.8 arc minutes in diameter. As you can see in the top right hand, the altitude only gets to around 20 degrees when viewed from Melbourne, LMDSS. So this is a bit of a tricky target for most of us to see, which is why it's so nice to have someone up north who can get us a bit more decent of an image. The next, another spectacular planetary nebula, M27, the Dumbbell Nebula. This one's located in the constellation Vulpecula at a distance of around 1,360 light years. Its magnitude 7.5, so pretty bright. And it's a little bit larger than the Ring Nebula at around 8 arc minutes in length and around 5.6 arc minutes in width. This one gets a little bit higher at around 30 degrees seen from Melbourne, still a little low if you're wanting to do any sort of long exposure astrophotography. SH2, Sharpless 2 101, the Tulip Nebula. This is part of the vast hydrogen nebulosity located in the constellation Cygnus. This one's at a distance of around 6,000 light years away. It's magnitude 9, and it's actually pretty modestly sized at around 16 arc minutes by 9 arc minutes. Again, this is a very, very low target for us here in Melbourne, but we'll be able to catch some views on Saturday. And just one interesting tidbit, which we'll talk about more in our live stream. If you look down on the left-hand side, the beautiful deep image by Ida Ivan. If you see that sort of blue sort of arc there, this is actually an arc caused by a nearby black hole that's sort of shooting out high energetic radiation. It's ionizing this sort of shock front. And we'll talk more about this if you're interested on Saturday.
I'm interested.
So
that's very cool.
Yeah, it's one of the more interesting targets. It's a real shame that we struggled to see it from Melbourne.
Well, we've got
NGC.
so good.
Exactly. The next one, NGC 6888, the Crescent Nebula, another one that I'm really kicking myself that I don't get to see from Melbourne. This is just an absolutely spectacular object. It's an emission nebula associated with a Wolf-Rayet star, which is a massive star that's sort of nearing the end of its life. It's a star that we think is going to explode in a supernova. But before it does so, it sort of ejected all of this mass and high energy radiation that sort of formed this really amazingly detailed bubble that you see on the left. It's around 5,000 light years away, magnitude 7.4, so pretty bright. And it's pretty modestly sized again, 18 arc minutes by 2 arc minutes. Next one, Pelican Nebula, IC 5070. This is another emission nebula located in Cygnus at around 1,800 light years, magnitude 8, and this is actually quite a massive object. Unfortunately, again, not really a chance that we'll get to see this from Melbourne. It only reaches around 10 degrees in altitude, but a really spectacular object for those Northern Hemisphere folk.
Stefan, I get the feeling we're going to put Caleb to work on Saturday night by the looks of it.
Oh, yeah, absolutely. And this is another one that in one of our previous live streams, Caleb got some shots of this for us. And this time again, I'm very hopeful we'll see some really spectacular shots from this. This is the giant Velar Nebula. This is a supernova remnant located in Cygnus, around 2,500 light years away. And its apparent size is around 3 degrees. So, 6 times the width of the full moon on the sky. But of course, incredibly dim. On the right-hand side, if you look at the simulated field of view, this is just covering it must be the eastern veil portion of the Veil Nebula. So as you can see, this is a really massive target, and there are some really popular sort of sub-targets within the Veil Nebula, the eastern veil, the western veil, and Pickering's triangle. And we'll be taking a look at all of these on Saturday. And yep, with that, that's about all that I could come up with in the night sky for this month. But yeah, again, if you want to see some more and some live images, please feel free to join us on Saturday.
That's a lovely little presentation there, Stefan. Thank you very much for that.
Thank you, Stefan.
Thank you.
So, Chris, did you have anything you'd like to add before we close things out for the evening? I've got a couple of messages, but
no, I think we're pretty well right. There's a few people getting up to the Dark Sky site this weekend, but it's not open at the moment. We've got some management people going up there for work purposes, but hopefully within the next week or so we'll be opening up the Leon Mao Dark Sky site for country members, and soon please for Melbourne members too.
Fingers crossed. Fingers crossed. We can get up there soon as well. But
yes.
Glad to see somebody's going to be able to use the Dark Sky site again from hopefully from next weekend if possible.
Yeah. They're mainly a work party going up there
this weekend. Yeah, it's been idle for a while, so
yes. So everything has to be checked out.
Yeah. Make sure it's all safe. Well,
Okay,
in that case,
over to you, Mark.
In that case, I just want to thank everybody for joining us this evening, and thanks Steffi for her wonderful talk, and Stefan for your presentation on some of the objects we're going to be looking at this weekend. So Friday night we have obviously the Lunar and Planetary live stream with a discussion on what telescopes to buy at the start of it. So don't forget also we've got raffle tickets for sale as well for an Ioptron iPolar mount for to use with a digital camera to do some wonderful nightscape images. It's been generously given to us by the team at Sidereal Trading. So thank you to Paul and Diego. And I need to say Bill as well now because he's there also. But yes, this weekend, starting Friday night, our Galactic Centre Star Party live stream extravaganza. And those of you who have seen some of the links going up may have noticed that we've gone with a 70s, 80s arcade game theme, ripped and edited and changed all of the lovely artwork from those games like Galaga and Asteroids and Space Invaders. So we're going to have a bit of fun with that. We're also going to have an astrophotography session where our new astrophotography section director is going to show you how to process the Trifid Nebula. We've got a solar session with Russell, our solar section director. We've got our first live stream instrument making section. We're going to have a couple of people from the instrument making section talk to us about their things that they've made from observatories in their backyards to telescopes. Also going to be talking about the All Abilities Astronomy Telescope as well. So you can actually get a chance to have a look at the telescope that we're trying to put up at our Dark Sky site for our wheelchair accessible members or people with mobility issues. There's going to be obviously Deep Sky that Stephan's been talking about. That'll be fun. And on Sunday, we'll have a Q&A panel. Steffi will be there for the Q&A panel. We have some other people coming along as well. And then closing things out on Sunday afternoon, we have a new astronomers live stream. So for those of you who are new to astronomy or want to get into astronomy, that's probably the perfect session for you to go to. One that you definitely don't want to miss because we'll talk about what you need to know when you're starting out in astronomy. So be sure to tune in for those. Links are on the Facebook and YouTube pages. Don't forget to our YouTube followers to switch the bell on. And if you're on Facebook, be sure to like our page. And to everyone who's donated stars tonight, thank you. It is greatly appreciated. We will see you at 7:30 on Friday night. See you later.
Thank you, Mark, and good night to you all. Thank